The next presentation is focusing on our sun, its activity, and the impact it has to our planet. So it includes a detailed description of the processes of the sun, the process of how the energy of the sun is transferred to our planet, and the effects on our planet. So I think also at the end there is some invitation to some activities for you to be involved in the process. Eleftheria Sotiriou from the National and Kapodestrian University of Athens has the floor.
Hello, everyone, and thank you to the organizers for the invitation. My name is Eleftheria Sotiriou, and I am studying physics in the National and Kapodestrian University of Athens. After I chose to direct my studies to astrophysics, I found my favorite course there, which was solar and space physics. And I am currently doing my bachelor thesis with Professor Ioannis Daglis on this field. It still is work in progress, but I am here today to share some parts of this work. Solar and space physics is basically research on solar system bodies, but for my presentation today we will emphasize on the Sun, the Earth, and their interaction with each other. Hopefully by the end of my presentation you will have a better idea of how a phenomenon like this, the aurora, is created. This is a picture taken from here in Greece, close nearby in Ceres, in November. And here a picture from Germany of the aurora, and here one from Iceland. Before we start, I have a question for you. It was kind of spoiled yesterday. So here on Earth we know that an Earth day lasts 24 hours, which is basically equal to the time needed for Earth to complete one rotation. Do you have any ideas how a Sunday lasts? In other words, the time that the Sun needs in order to complete one of its rotations? Okay. 27 days. Okay. Yes? Sorry, 50 days. Yes.
I think it depends on the longitude of the sun. Some areas are rotating faster.
Okay. Okay, that's great. So it is up to the place on the Sun's surface. As you probably know, the Sun is not solid, so its rotation is differential, as we call it. If we are around the equator of the Sun, then one rotation lasts 25 days, close to 27. But if we are around the poles of the Sun, it takes 10 days longer for the Sun to complete one rotation. Let's now talk about some more general characteristics of the Sun. As you can see from the first picture here, its diameter is pretty big, and if we put many Earths there, we would need 109 Earths in order to fit to the diameter of the Sun. Its mass is 333,060 times the mass of the Earth. The maximum temperature reached inside the Sun is in its core, and it's about 15 million degrees Celsius. Our sun is 4.6 billion years old, and it's supposed to live for another 4.6 billion years before it dies, as you also heard yesterday. Another important information before we move on from this slide is that the distance between the Earth and the Sun is 150 million kilometers, and as you also heard before, the light from the Sun needs 8 minutes to travel this distance and reach our eyes on Earth. Now let's talk about the anatomy of the Sun. First of all, nowadays basically the Sun consists of hydrogen and helium. And we will divide the Sun in two large parts in order to talk about it a bit more easily. So we firstly have the interior of the Sun, its inside, which is not visible to us at all. And then we have the outside of the Sun, which is the only part that we can actually see. Starting from the inner part of the Sun, we firstly have its core in the middle, as you can see here, where hydrogen's combustion into helium takes place, and this is how energy is generated there in the form of light and heat. This energy generated in the core is traveling at first through the radiative zone via radiation. This is why it's called the radiative zone. But moving outwards, it reaches a point where it can no longer be transferred via radiation, and this is the convective zone. As you can probably imagine, the closest we are to the core in this zone, so the inner part of this zone, has higher temperatures than the outer part of this zone. This is why hotter plasma is traveling from deeper areas of this zone closer to the surface of this zone. And those that I just described are called convective currents, as you can see with the arrows here. It's just the motion that I described. And because of this circular motion that the plasma is doing there, they are called convective cells. Next, well, in this zone here, due to these convective turbulent motions, and also due to the differential rotation of the Sun that we talked about, happens the generation of the solar magnetic field. Sorry. Okay. We now turn to the visible part of the Sun. Firstly, the photosphere of the Sun is what we can actually see as the Sun's surface. Followed afterwards by the chromosphere, where a dramatic decrease of the density of the plasma takes place. The transition region afterwards connects the chromosphere with the corona. And then the corona, well, if you have ever seen pictures of a total solar eclipse, then the corona is the only part of the Sun that is visible during that time. There are also satellites and spacecrafts currently orbiting or observing the Sun who have this telescopical attachment called the coronagraph. I will also show a picture later in the presentation, which basically hides the disk of the Sun, well, because it's kind of blinding, and that's how we can actually see what is happening around it in the corona. Last but not least, we have the heliosphere, which ends at the so-called heliopause. Well, it's not here in the picture because it wouldn't fit in it. It reaches too far away. to the point where the existence of the sun could no longer be felt by something there. If someone wanted to travel to this point where the heliopause is, they would have to travel 123 times the distance between the sun and the Earth. And the only two spacecrafts who have achieved that goal are the Voyager 1 and Voyager 2 missions. In the surface of the sun, the photosphere, as we talked about, appear two structures that we are going to discuss. As you can see, here, firstly, we have the sunspots. And as you can see from the picture, they are darker spots on the surface of the Earth. This darker color shows that their temperature is really low compared to the other parts of the sun. And from those sunspots, magnetic field structures emerge. And those structures, like loops, they are called prominences, like here. I also have a realistic picture of one of these so that you can see how huge this structure is. Here, the Earth is just added in the picture so that you can compare the size. It's important to mention here that this loop that you see is not the actual magnetic field line because those are invisible, but it just is the plasma, which is the hot gas with which is full of charged particles that is traveling around the line, and this is what's visible here in the picture. From observations, astronomers knew that the number of sunspots and prominences seemed to increase and decrease, and that's how they started to view it as a circle, a so-called solar cycle. Sorry again. Here you can see a collage, basically, of many pictures of the sun, taken one each year of one solar cycle, the 24th solar cycle, and the number started counting from when we actually have data in order to call them solar cycles. So here you can basically see that in the years, for example, 2014 and 2015, the sun has many more sunspots, many more prominences, and seems more active. While there, for example, 2019 and 2020, the sun seems more calm. Not so many sunspots and not so many prominences. And so I have a graph next. Please don't freak out with the graph. I will just explain the most important parts. So here on the horizontal axis, we have the year number starting from 1965. And on the vertical axis, we have the sunspot number. As you can see, every about 11 years, there seems to be a maximum here at the number of sunspots. This is how long a solar cycle lasts, 11 years. So every 11 years, we have a maximum. Today, we are in solar cycle 25. And this year and the next year is, as you can probably see, predicted to be its maximum. Let's look now at 2019, for example. Do you see it being a minimum or a maximum? Okay. What about 2014? Yes. Okay. So let's move on to the next slide, where two pictures of the sun from the years that I just asked you about are shown. The first one is from 2019, as well as you said, it's a minimum. And the second one is from 2014, as well as you said, it's a maximum. You can see the difference, I think. The prominences and sunspots are many more appearing in 2014 when it's a maximum. I also have the same picture. The previous one was in UV, and this is in visible light, so that you can actually see the sunspots, those darker spots, as we talked about in the solar maximum. Okay, so during the solar maximum, there are explosive events happening in the sun. Two of them are the most important, I would say, and we will talk about them today. Firstly, there are solar flares, and secondly, and most importantly for today's presentation, are coronal mass ejections. Yeah, they do appear here, but I will show them again in a bit. So solar flares are basically a sudden release of energy, mostly in the form of light. But in one of the first slides, we talked about how much time light needs in order to travel to Earth, which was 8 minutes. So if a solar flare happens right now in the sun, someone with the right equipment and a bit of luck may be able to see this flare from Earth after 8 minutes. It's important also to say that since it's light, it is traveling to every direction. Let's now move on to coronal mass ejections, or CMEs. These are large explosions of plasma and magnetic field from the sun's corona. This is, as I mentioned before, a coronagraph picture, where the disk of the sun is hidden so that we can see only the corona and capture events like that. Since all of this plasma and magnetic field together has a mass larger than the mass of light, which is 0, it needs more time to travel to Earth and reach Earth. If it's a very fast coronal mass ejection, it takes 15 to 18 hours, very fast, once again. But normally it takes 1 to 3 days to reach the Earth. Now here is a picture that probably will help you understand the difference a bit better. As you can see here, a coronal mass ejection has this loop structure, while the solar flare has no such thing. Well, before we watch the video, those two events, explosive events, might also occur together in the same region of the sun at the same time, but they are not always related. Let's watch a video now that will probably help you understand the difference even better. Okay. Δεν έχω ήχο. Είναι μέσα. Όχι όλα. Το έχω δυναμώσει. Ναι, να μην είναι σε αυτό. Θα ακουστικά μου. Shift F5 τώρα. Δεν θέλω να αλλάξω και το... I hope the difference was made a bit more clear by the video. So now let's leave the sun for a bit and return to our planet. Earth has a huge shield, as you can probably also see in the background here, but it's easier here in this picture. And this shield, it's called the magnetosphere. Let's now imagine that inside of the Earth we have a huge magnet. Its core, it's like a huge magnet, and this magnetic field is created. As you can see, there are two places on the planet that are not really protected from this shield. And those are its poles, here. Okay. As sorry again. So this picture shows a perfectly dipolar magnetic field, but Earth's magnetic field is not exactly like that. From the day side, the side that faces the sun, it seems like the previous picture a little bit, but on the other side a tail is formed, which is called the magnetotail. And this is the magnetic field basically extending due to solar wind far away from the planet. Solar wind is a stream of charged particles that is released from the sun's corona. Let's now, I will show you a video again that will basically explain the interaction between the sun and the Earth that we are talking about. Okay. So this video basically ends with explaining how the aurora is created, and this is why it has some clips here in the start. Everything is starting from the sun. I will repeat some of the things that I previously said so that you are watching them at the same time, because I think it helps understand more. Sorry? That's the sun, yeah. Well, what you will see, it's not really real because you see we just have like a hole here so that you can understand it better. But you will see. On the inside of the sun, as we talked about, energy is generated in its core, where the temperature is really high, and also pressure is very enormous. It's so enormous that hydrogen atoms, as you will see, are squeezed together, forming helium. And this nuclear reaction is what generates the energy inside the core. The light travels towards the core of the sun, firstly via the radiative zone, as we talked about, and then the convection zone. These currents of charged gas create a magnetic field inside of the sun. In some places, strong magnetic fields push their way through the surface, and the area around the line cools down, and this is how the sunspots appear. The plasma carried by the magnetic field drags the magnetic field further outwards, and at some point it stretches so much that it breaks, as you saw. Now, a huge mass of plasma captured in magnetic field lines starts traveling around in our solar system through space, which is what we name CME. This huge structure can travel with speeds from 200 to 3,000 kilometers per second. If it's really fast, after 6 hours, as you can see, it will reach the orbit of planet Mercury. After 12 hours, the orbit of Venus. And again, if it's really, really fast, in 18 hours, it will reach the orbit of our planet, and maybe even our planet at this point. And this is where this solar storm meets the Earth's magnetic field. As you can see, the magnetic field of the solar storm and the magnetic field of the Earth have opposite directions, as you can see from the arrows. The blue arrows are headed upwards, while the yellow arrows are headed downwards. Earth's magnetic field is always like that, but the solar storm's magnetic field, so the yellow arrows, could also have the opposite direction, viewing upwards like the Earth's magnetic field. And if that were the case, none of the following things that we're going to talk about would happen. But since that's not the case, and they are in opposite directions, let's now see what follows. The Earth's magnetic field lines on the day side break, and they reconnect with the magnetic field lines of the Sun, which now has plasma particles, high-speed particles, getting inside the magnetosphere. Now, the new lines that are formed are traveling backwards to the magnetotail. So normally there are more lines in the magnetotail, but just so that you can understand it better, they are not here right now. So those more lines that I talked about are the ones squeezed, and they will break again and reconnect with each other, accelerating those particles in those lines towards the Earth. Those particles are traveling along those magnetic field lines, and as you can see where I stopped it, they are traveling towards the poles of the magnetic field of the Earth. Okay, which are unshielded, as we talked about. There is no protection, not as much protection there. And this forms the aurora. And some videos follow of the aurora. Here is also a picture of what we just saw through this video. This time the solar storm magnetic field is with a blue arrow, and Earth's magnetic field with yellow arrows. As you can see, the lines will reconnect here with the solar storm's magnetic field and travel backwards, where they will reconnect again and accelerate the particles into the inner magnetosphere. We will move closer to the aurora and the poles of the Earth in a bit, but before that we will talk about how strong a magnetic storm could be. Of course, there are stronger ones and not the strong ones. So how do we categorize them? There are 4 observatories around the globe, and all 4 of them are efficiently away from the poles of the Earth, which are, as we said again, the unshielded areas. Those observatories are measuring the magnetic field on the surface of the Earth, And basically the relative change of these values is called the DST index. And this is what we used in order to categorize the storms from stronger to not that strong. This is a diagram here. On the vertical axis we have the values of the DST index, and on the horizontal axis we have the day of year. I chose here 10 days starting from the 10th of May, when you might have heard that there was a big solar storm happening, and also auroras in lower latitudes were visible. So starting from here, early on the 10th of May, we see that the values are around 0. So if there was no no magnetic storm happening, those values would stay this way for the whole period of those 10 days. But as you can see, during that day, there was a little increase here in the values of the DST index, which happened when the reconnection in the day side of the magnetosphere happened. And this is called the initial phase, or storm sudden commencement. This phase is followed by a huge decrease, as you can see here, of the DST index, which is happening during the acceleration of particles, which are now drifting around our planet, creating a magnetic field that is headed to the opposite side of Earth's magnetic field, and this is why it seems like a decrease on the diagram. And this is called the main phase of the storm. The minimum of the DST index down there is basically the value that shows us if it's a strong storm or not. On this day, it reached about minus 420 nanoteslas, which makes it a really strong storm. It's a G5, as I have written up there, on a scale from 1 to 5, with 5 being the strongest. So the following days, after a very strong storm like that, comes the recovery phase, when in which time the magnetic field basically tries to return to its initial normal values. Two notes before we move away from this slide. As you can see, the 9 days here was not really enough time for this storm in order to for the magnetic field to recover completely. So here it's not really 0 yet. And the second thing is that the Earth's magnetic field is not 0. The thing that it's the values of the DST index are 0 here is because the magnetometers are calibrated around this number, so that we can only understand the change and not the real values of the magnetic field. Let's now move back to the aurora. In places with higher latitudes, the aurora seems like that. How many colors can you see here? Yes. Okay. As we saw in the video, I kind of stole a screenshot of it so that I can remind you that particles are accelerated from the magnetotail and traveling through the poles, to the poles. The atmosphere basically consists of oxygen and nitrogen. So as you will see in the workshops later this week, When a high-speed electron, this is the electron coming from the magnetotail, accelerated, and this is, for example, an atom in the atmosphere that it will meet. And when it hits this atom, the electron gets part of its energy and it's excited, as we call it. But this is, as you can see, an unstable state. So after a short period of time, this electron will return to its initial phase, and the excess energy will leave as a photon. And this is the light that causes the aurora. Okay. Starting from lower heights, electrons that enter the atmosphere meet nitrogen atoms there, and they create those two colors, or even a kind of a pink shade sometimes. Accelerated particles also meet the oxygen atoms that we talked about, and they create green colors or red colors if we are higher. Well, some of you may be wondering right now how oxygen atoms can also have us seeing green and red light at the same time. So the thing is that in order to see red, we need electrons with more energy. And that's why it's only in higher heights, because as we get deeper in the atmosphere, the atmosphere is more dense. So the electron coming inside will meet many more atoms and collide many more times, so it will lose its energy and it will not have as much energy to give to the oxygen atoms. Okay. Sorry. The lower edge of the aurora is usually about 80 to 100 kilometers, and the upper edge is usually at 250 kilometers, but in some more rare phenomena it could reach 500 to 800 kilometers. You can also see here, in order to compare the height, the Mount Everest and an airplane. So now, I don't know, were any of you that lucky in these last huge storms to see the aurora? Maybe? Anyone? Oh, really? Okay. So now this next thing I say might disappoint you a bit. I'm sorry in advance for that. But down here, the aurora isn't really over our heads. What we actually see is the top of the aurora here, as you can see from Thessaloniki, for example. And we see the aurora created above Finland. This is why in lower latitudes only red color is visible. Okay. Here I also have, for example, a picture from different latitudes with the as shown aurora pictures, and we see that in higher latitudes we see many more colors, for example also green, and as we go down, the only color that is now visible is the red color. I also have some pictures of the aurora taken from space. And it's important to say that along this beautiful, let's say, light show that we see with magnetic storm, we can also have consequences. like interference with radio communication, GPS systems, or electricity. For example, in 1859, there was a big event called the Carrington event, and it caused problems with the technologies then in use, which was the telegraph. High-speed particles, well, this is not about solar storms, but it could also happen with solar flares that we mentioned, but we didn't keep talking about them. So, when particles, anyway, high-speed particles travel in space, they are dangerous for astronauts out there, and also even for satellites and technologies. So it's important to be able to predict, I would say, but we're not really able to do that yet when such an event will happen. So now, closing, I want to say that there is a number of citizen science projects. For example, if you're interested, you could also see here. One of them is the Aurorosaurus, where you can report if you saw the aurora, like you did, and the location that you saw it from, and some of the details, for example, if it covered the whole sky, if it didn't, if it covered half of the sky, and stuff like that. And projects like that help the scientific community to have a more accurate knowledge, I would say, about the aurora. Here is a picture, for example, from May 10th, as the diagram that I showed you before from the solar storm G5. And this is all the people that went into this website and wrote that they saw the aurora. You can see there are kind of many, but here in the Balkans we don't have that much support. So you can also visit this website, and if we are lucky enough again, but it's a solar maximum now, so maybe we will be lucky again, in order to have a storm that we can actually see the aurora from. And this is pretty much all, so thank you. And yes, and I'm here for your questions. Yes. I can't hear anything.
They predicted that that there is going to be a solar storm at I think the May of 2025, and I wanted to ask if it would be true. Some scientists predicted that.
Okay, so I don't think that the prediction was about a specific solar storm, but since it's a solar maximum, there are about to be many solar storms in that time. So yeah, I don't think that it has a date or something like that, but it's really possible to happen in the next year, yes.
Previously, at around the start of your talk, I saw an infographic that said that the sun's magnetic field essentially flips every 11 years. Is this related to the solar cycle of sunspots or not? Or is this just a coincidence?
No, I don't think it's a coincidence.
And is there like any relation between the two actually or not?
I mean, I'm not really sure when exactly in those 11 years this happens exactly. I will check something that I need to know, and I will come right back to you after in the break.
Thank you.
Okay. Oh, okay. It's not on.
What effect could a solar storm has on us if the magnetic field breaks?
Well, I have good news for you. It won't break. But if we didn't have the magnetic field, we would probably be like the other planets in the solar system with no life here. So the air would not be able, the Earth could not be able to keep the atmosphere that much, so it will fade. And you understand afterwards that it's not really, yeah.
Thank you.
But this won't happen, so.
Why Earth has a different magnetic field from other planets?
What do you mean different?
I mean, as far as I'm concerned, Mercury and Venus also have magnetic fields, just not the same as Earth's. I mean, if it doesn't affect Earth and affects the other planets, there must be something different about Earth's magnetic field.
So
do we know why
it's stronger, what you were saying, it's stronger. And it has to do with the core of the Earth, I think, because the material there is what basically is like this imaginary magnet that I talked about, and this is what is creating this stronger magnetic field. So the core is different, the magnetic field is different. We are luckier, so that's it. May I ask you too something? Where did you see the aurora from?
From my neighborhood.
Yeah, where?
Menemeni.
Okay. Any other questions? Oh, up there again. Ah, here too.
From the map that you showed us, we could see that the observatories, all 4 observatories, are close to the equator.
Yes.
Is that to minimize interference?
Yes. This is why it's efficiently, as I said, away from the poles where they are unshielded, and we could have many more interferences there, so that's why.